Welcome back, students. This is the session 16 from the playlist of electric charges and fields. The topic is the derivation for measuring the electric field at a point due to uniform charge distribution on a thin spherical shell. So here I have already made one diagram here. So this is the thin spherical shell, and there is a uniform charge, positive charge distribution on the outer surface of this thin spherical shell, and I have taken the sigma as the uniform surface charge density on the outer surface of this thin spherical shell. Now I am supposed to find the value of electric field at a certain point outside this spherical shell due to this uniform charge distribution. So I have taken the point P which is outside this thin spherical shell, and it is situated at a distance small r. The radius of this thin spherical shell is capital R, and the this uniform surface charge density is equal to sigma. So I will be using the Gauss law in order to find the magnitude of the electric field at this point P, which is situated at a distance of small r from the center of this thin spherical shell. Now as per the Gauss law, the flux through a closed surface, this is a closed surface, the flux through a closed surface is given by Q divided by epsilon naught. Here I am considering that this thin spherical shell is present in free space. So if this thin spherical shell is present in free space, then, or you can say if any object, okay, or you can say if any closed surface is present in free space, then the flux through that closed surface is equal to Q upon epsilon naught, where Q is the total amount of charge which is enclosed by that closed surface. So I will be using this concept in order to derive the value of the intensity of electric field at this point P, which is situated at a distance of small r from the center of the thin spherical shell. So now the first step is to construct the Gaussian surface. We have to construct a Gaussian surface. As I have made it here with the help of this dotted line, and this Gaussian surface has to be made in such a way that the point at which we have to find the value of this electric field should be enclosed by it. So I have constructed a Gaussian surface in which this point P is enclosed by it. Okay. Now this is the first step. Construct the Gaussian surface. Construct a Gaussian surface. So I have already constructed this Gaussian surface. Now I will be using the Gauss law. Now as per the Gauss law, the flux through a closed surface is equal to Q upon epsilon naught, where Q is the total amount of charge which is enclosed by that closed surface. So here this Gaussian surface is the closed surface, and I have to find the total amount of charge which is enclosed by this Gaussian surface. So here I have taken this sigma as the surface charge density, okay, of this uniformly distributed positive charge on the outer side of this thin spherical shell. So sigma will be equal to Q divided by, sigma is what? This is equal to the charge per unit area. So this will be equal to Q divided by, now the area of this spherical shell will be equal to the surface area of this thin spherical shell will be equal to 4 pi r square, where capital R is the radius of it. So from here, the total charge which is distributed on the outer side of this thin spherical shell will be equal to sigma into 4 pi capital R square, and this is the amount of charge which is enclosed within this Gaussian surface. So so in the first step we have to construct a Gaussian surface. In the second step we have to find the total charge. We have to find Q within the Gaussian surface. Okay, we have to find Q, that is the total amount of charge which is enclosed by that Gaussian surface. So that I have already found, which is equal to sigma into 4 pi capital R square. Now the third step. In the third step, I will be using the another formula for flux, which is equal to Es cos theta. Okay. Now here, so the flux through a closed surface is also equal to Es cos theta, where theta is the angle between the direction of electric field and the normal to the surface. Okay, and S is the surface area. Here S will be the surface area of this Gaussian surface, and E is the intensity of the electric field, and so phi will be equal to E. Here the surface area of this Gaussian surface is equal to 4 pi R square, and now here theta is the angle between the direction of E and the normal to the surface. So let us say at this point, at any point on this Gaussian surface, the direction of the electric field will be directed outward radially. Okay, like this. Let us consider this point here. So this is the direction of the electric field, and this will be directed radially outward. And at this point, the normal will be here. At this point, what I am doing is I have drawn one tangent here, and the normal to the surface at this point will be perpendicular to this tangent. This is the tangent at this point, and the perpendicular to this tangent means, see, this is the perpendicular to this tangent. So this is the normal to the surface at this point. So you can see from this figure that the direction of E and this normal to the surface is the same. That is, both are parallel to each other, and when they are parallel to each other, then theta will be equal to 0. So if theta is equal to 0, then cos theta will be equal to 1. So phi will be equal to E into 4 pi R square into 1, because cos 0 is equal to 1, and as per the Gauss law, phi is also equal to Q upon epsilon naught. Okay, so I will be using this will be equal to Q upon epsilon naught. The value of Q is equal to, so it implies that E into 4 pi R square will be equal to, the Q is equal to sigma into 4 pi R square divided by epsilon naught. From here, this 4 pi and 4 pi will get cancelled out. So the value of E will be equal to sigma R square divided by epsilon naught into R square. So the intensity of this electric field at you can say at any point on this Gaussian surface will be equal to sigma capital R square divided by epsilon naught into small r square. So this is the value of the intensity of electric field, and this is the value of the intensity, and this is the value of the this electric field at any point on this Gaussian surface. So we can say that the value of the intensity of electric field at this point P will be equal to sigma r square divided by epsilon naught into small r square. So here you have to use the concept of the Gauss law, and with the help of the Gauss law and the formula, that is Es is equal to cos theta, we were able to find the value of the electric field at this point P, which is lying outside this thin spherical shell. So I hope that you must have understood the derivation of this electric field due to this uniformly distributed charge on the outer side of this thin spherical shell at this point P. And in the next session I will be coming up with a couple of questions which will be based on the Gauss law. So till then, have a nice day. Bye.